Okay, welcome back, students. Let's cover 9.3. Okay, 9.3, general results for first order linear systems. Okay, okay, theorem. Okay, the initial value problem x prime of t equals a of t times x of t plus b of t, where x t naught equals x naught, where a of t and b of t are continuous on interval I has a unique solution on I. Okay, homogeneous vector differential equations. Okay, x prime of t equals a of t times x of t, where a of t is an n by n matrix function comma, has a solution if there exists a combination of n linearly independent solutions x1, x2, dot, 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 xn. Okay, that form a basis for the solution space. The general solution will take on the form okay, x of t is equal to c1 x1 plus c2 x2 plus dot 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 cn xn. Okay, notice there's no b of t in this because it's homogeneous. B of t would be zero, would be the zero vector. Okay, definition. Any set of n solutions x1, x2, whoops, xn to x prime is equal to ax. That is linearly independent. Is called a fundamental solution set. And the corresponding matrix x of t equals x1, x2, is called its fundamental matrix. Dot xn is called its fundamental matrix. Okay, theorem. Let A of t be an n by n matrix function that is continuous on interval I okay, if x1, x2, dot, 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 to xn is a linearly independent set of solutions, is a linearly independent set of solutions to x prime equals ax on I, then the Wronskian of x1, x2, dot, 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 xn of t is not equal to 0 at every point in t. Let me see, every point of t in I. Okay, let's do an example. Number 1, consider the vector differential equation x prime equals ax, where a is equal to 1, 2, negative 2, 1. and let x1 equal negative e to the t cosine 2t and e to the t sine 2t, and x2 be equal to e to the t sine 2t and e to the t cosine 2t, period. Verify that x1 and x2 are solutions to the differential equation, and find the particular solutions or sometimes they're called scalar solutions, when x of 0, okay, when t is 0 is equal to 3, 2. Okay, so let's do part A here, which is seeing if x1 and x2 are solutions to this differential equation. So x1, we want to know if x1 prime is equal to a times x1. Okay, so what is x1 prime going to be? Well, x1 prime is just going to be the derivative of the elements. We want to know that's going to be product rule. So that's negative e to the t times cosine 2t plus derivative of cosine is negative sine, so that's plus e to the t, 2e to the t sine 2t. Okay, and then this is going to be e to the t sine 2t, derivative of the first times the second, plus derivative of the second, which is 2 e to the t cosine 2t by the chain rule, product rule and then chain rule. Okay, does that equal, basically we're asking a question, does this equal a, which is 1, 2, negative 2, 1, okay, x prime 1, does that equal a times x1? And x1 was negative e to the t cosine 2t e to the t sine 2t. Okay, so let's see. This is going to be 1. If I do matrix multiplication, this is going to give me this guy times this guy first. So this is going to be equal to negative e to the t cosine 2t plus 2 e to the t sine 2t. Okay. And then we'll do the second row times the first column, which is going to be negative times negative, which is a positive. Okay, positive 2e to the t cosine 2t. Okay, and then this is plus e to the t sine 2t, which is in fact the same. That checks. Okay. Now let's see if the other one, x2, works. Okay, so x2 prime is equal to ax2. So what's x2 prime? Okay, what was x2? x2 was e to the t sine 2t. Okay, e to the t sine 2t, e to the t cosine 2t. So this is going to be e to the t sine 2t. Okay, plus 2e to the t cosine 2t. Okay, and then that's going to be e to the t cosine 2t minus 2e to the t sine 2t. Okay. Okay, and we're going to say, does that equal a, which is 1, 2, negative 2, 1, times x2, right? So this is x2 prime. Okay, does that equal x2? What was x2? It was e to the t sine 2t and e to the t cosine 2t. Right? Okay. So now let's just multiply this together. Okay, and we get e to the t sine 2t plus 2e to the t cosine 2t. So that's good. Okay, first row, first column. Okay, and then the next one, second row, second column, that's going to be negative 2 e to the t sine 2t, and then plus e to the t cosine 2t, which does work. Okay, so that does check as well. Okay, so those are solutions. Okay. Okay, so okay. Verify that they are solutions and find the particular solutions when okay, so let's go back to, okay, let A of t be an n by n matrix function that is continuous on a raw line. If x1, x2 is a linear independent set of solutions, then the Wronskian every point. Okay, so I want to know if these solutions are linearly independent, or are they just a combination of each other? Is there really an x1, x2, or is it just an x1 and x2 is just a multiple of x1? Okay, so yeah, because the definition, any set of n solutions that is linearly independent is called a fundamental set. So let's show that these are solutions, that they're, well, they are solutions, we know that, but are they first linearly independent solutions? Okay, and that will help me write the general solution, and then I can write the particular solution. Okay, so let's find the Wronskian of these. Okay, so let me rewrite what x1 and x2 was. x1 was negative e to the cos 2t and e to the t sine 2t. Okay, x2 was equal to e to the t sine 2t and e to the t cosine 2t. That's correct, right? Yep. Okay, now I want to know if these are linearly independent. Okay, so let's take the Wronskian of these. And we'll find the determinant of negative e to the t cosine 2t and e to the t sine 2t, e to the t sine 2t, and e to the t cosine 2t. Okay, this is going to be equal to negative e to the 2t cosine squared 2t minus e to the 2t sine squared 2t. Okay, so that's going to be equal to negative e to the 2t, okay, times cosine squared 2t, oops, plus sine squared 2t. Okay. And this thing is equal to 1, so this just equals e to the negative e to the 2t, okay? And is there some t naught? If I let t naught equal 0, well, then that just becomes negative 1, which is not equal to 0, okay, which tells me that they are linearly independent on negative infinity to infinity. So linearly independent on negative infinity to infinity. Okay. Okay, and since there's two, okay, two of each here, two components in each vector. Okay. Okay, that tells me that I could write the general solution, okay, x of t, okay, as c1 times x1, oops, c1 times x plus c2 times x2, okay? Since they're linearly independent, okay, if they weren't, then I couldn't do that. Okay, so this is the general solution. I don't know if this goes back to our definitions. Yes, homogeneous. So the definition of homogeneous, okay, is if there exists a combination of linearly independent solutions, okay, that from a basis for the solution space, the general solution will take on this guy here. Okay, so we're just saying, hey, that general solution is going to look like that. Okay, and so this is going to be x of t is equal to c1 times x1, which was negative e to the t cosine 2t times e to the t sine 2t, okay, plus c2 e to the t cosine 2t times e to the t sine 2t. I think that's reversed, actually. E to the t sine 2t and then e to the t cosine 2t. Okay, and this is the general solution. Okay, so you could say that x1 x1 of t is equal to c1 or negative c1 e to the t cosine 2t okay? And then plus C2 e to the t sine 2t, and x2 t is equal to c1 e to the t sine 2t plus c2 e to the t cosine 2t. Okay, and they're saying that when we plug in 0, okay, into this, okay, and we could think of this like a matrix, okay, so this guy would be x of t, my two solutions, okay, x of t, okay, is equal to this guy. They're saying when we plug in 0, get x of 0, we end up, okay, x of 0, we end up with 3, 2. Okay, so going back to the original original problem, okay, it says when the solution, we plug in 0 for t, we get out x1 equaling 3 and x2 equaling 2. Okay, so we'd say this guy is equal to negative c1 e to the t cosine 2t plus c2 e to the t sine 2t. Okay, and then c1 e to the t sine 2t plus c2 e to the t cosine 2t. Okay, equals, when we plug in zeros into all that, that equals 3, 2, right? So let's just plug in the zeros. 0, 0, 0, okay, 0, okay, 0, and 0, 0, last one, 0. Okay, so now anything that involves a sine is going to go to 0. Anything that involves a cosine is going to go to 1. And anything that involves an e is going to go to 1. So this just becomes negative c1 is equal to 3. So c1 equals negative 3. Okay, that's easy. That's from the top line. The other one is the sine of 0. This whole thing just goes to 0. Okay, the first term just goes to 0. Second term here went to 0. So c2, this whole thing just goes to 1. This whole thing went to 1. And so I'm just left with c2 equals 2. C2 equals 2. Okay, so what are my solutions? My solutions are x1 of t is equal to 3, okay, because it's negative c1. I'm looking at this line here, okay, and that line there. It's negative of c1, which is the negative of negative 3, which is 3. Okay, so this is 3 e to the t cosine 2t plus 2 e to the t sine 2t. Nice, nice, nice. Okay, and then what's x2? It's just negative 3 e to the t sine 2t plus 2 e to the t cosine 2t. And that's my particular solution. Whereas this thing up here is my general solution. Okay, and we could get rid of the matrix bars. Okay, so we have a general solution and we have a particular solution. Okay. Okay, looks pretty nice. Okay, let's stop there. And I'll see you in the next section.